All right, recorder back rolling. We're near the end of class. I'm gonna go ahead and debrief this with you guys. See how close you guys got here. So for the free body diagram, did you guys draw upward force, downward force? The downward force is the weight. The upward force is the buoyant force. Buoyant force breaks down to density of the water times the volume displaced times gravity field. Right? The weight is mass times gravity field. Right? Okay, so those are the opposing forces, right? And it reaching an equilibrium. Density of water, you call 1,000, I'm so sorry, oops, just one, right? 1 gram per cubic centimeter or 1,000 kilogram per cubic meter. Right? Wait, did I say that at the beginning of class? I think I said at the beginning of class. Talking about right? How many grams in a cubic centimeter? How many kilograms in a cubic meter? Right? And gravity field. You could go 980 or 9.8 meters per second squared. I'm going to round that up a little bit to 1,000 centimeters per second squared, or about 10 meters per second squared. That's rounded up a little bit. Okay. All right. Then expression for y in terms of x. Do you guys see the more you fold up the side x, the smaller y gets, right? In fact, if you start with 12 centimeters and you fold up by some amount x on both sides, don't you have to subtract that from both sides? So it's like 12 centimeters minus 2x, right? That's that, okay? That's that constraint right there, right? The more you fold up x, the smaller y gets, right? What's the volume of the box? Well, guys, what's the volume of the box in general? Isn't it base times, okay, so length times width times height, right? Length, width, height. So that's y times x. That's like y squared times x, right? Y times x. Isn't that true? Okay. Then, now this y and this x are not independent of each other. Y depends on x. That's what the previous equation says. So you can do a substitution and get what is the volume of the box strictly as a function of how much did you fold to each side. So here's what I showed you guys yesterday. Oh, look, boing, boing, do a substitution. Did a little FOIL, first outside, inside, last, distribution, boing, comes to this answer right here. So here's the volume of the box in cubic centimeters as a function of how much should you fold outside x in centimeters. Right. I'm just gonna go ahead and copy that right here. Right. So let me say 144x minus 48x squared plus 4x cubed. Now keep in mind, of course, that's all in centimeters. So this would be, see, square meters on the 144, plain centimeters on the 48. Okay, and then unitless on that 4. So, okay, like that. Now if you're trying to maximize the weight that the boat can hold, isn't that like trying to maximize the speed? Because the density of the water is whatever it is, gravity field is whatever it is. So if you want to maximize the buoyant force, you need to maximize the volume of the boat. Now, this step right here says calculus students can, at this point, use calculus to optimize the size of the boat. I'm going to do the calculus right here. If you're in calculus, know what I'm doing. If not, don't worry so much about it. But it's like this. Volume is, I'm going to copy that equation. 144, I'll drop the units just for a moment here. Minus 48x plus 4x cubed. All right. There's the volume of the boat as a function of x, how much you follow each side. Right? And now, if you're trying to get an optimal volume, I'm going to kind of hint towards towards this graph on the back. It says, what is volume as a function of x? And I was kind of hinting towards you guys at the beginning of the class. It's going to be some kind of upside down curve, which is not a parabola, but somebody did that. Now, guys, if you hold your, can you guys imagine this curve? I'm going to draw it by the end of class, right? Kind of an upside down-ish curve. If you hold your ruler like flush to this curve, right? Use imagination right now. There's some point like at the top where it goes flush with the curve that's horizontal, right? Isn't that true? Right. So you can say the rate change of volume with respect to x would be 0. The slope is 0, right? So like it's increasing leading up to it. The more you fold, the bigger the box. But at some point, it's going to decrease. So I need to find where the rate change is 0. And that is where the calculus comes into play. I can say the rate change of volume with respect to how much you fold at the side x. Right. Right. Now here, I'm going to use a little calculus trick to get what's called, this is squared. X plus 12x squared, right? And I'll set that equal to 0, right? Then you can just go back to algebra and solve for x. Ooh, you guys think you could solve that for x? That is solvable, right? I'm gonna kind of skip a little bit here and kind of reveal the answer, right? The answer ends up being 2 and the unit is centimeters. Let me prove that to you guys. If I take 2 and I plug it into here, this should 0 out. See if it does. That's 144 minus 96 by 2 plus 12 by 2 squared. Right? Yep, it's 0. Right? Remember what that means. That means that the rate change of volume with the changing x is 0, which means it's neither growing nor shrinking, which means that you found an optimal value. Okay. Right. Okay. So now, if you ever take calculus one day, it's like, oh yeah, I remember like box boats, and you might be given this exact question in calculus class too. Right. But right, let's go back to just like brute force trial and error method. Right? What if I try like x is 1, 1.5 centimeter, 2, 2.5, 3. You could try different values. What would y be? Well, you could just use this constraint right here. Right. The more you fold up x, the smaller is y. 12 minus 2 by 1, that's 10. So now you have the base that's 10 by 10 for a height of 1 centimeter. Right. If I take that to 2, 12 minus 2 by 2 is 12 minus 4 is like 8 by 8 base. Right. 3 be 2 times 3 is 6. 12 minus 6 is 6. Right. Kind of fill in the middle here. I bet this would go something like this, right? Right. So you got a shrinking base with a growing height of your box. Right. What's the volume? So volume could be y squared times x. So 10 squared times 1, that's like 100 cubic centimeter. What's 9 squared times 1.5 is 121.5 cubic centimeter. 8 squared by 2, 128 cubic centimeter. Look at that. The more you fold up the side x, the box is growing bigger, bigger, bigger. Let's try the next set. What's 7 squared times 2.5? Ooh, it went down. Ooh, look at that. And then 6 squared times 3, yeah, 108 cubic centimeters. So that's the volumes of these boxes. Guess see how first the box grows bigger, and then if you fold it too much, it starts growing smaller, shrinking smaller. Is that right? One more step here. What is the buoyant force? Okay, so that's rho VG, right? All right, so let's try that. I'm going to focus on this one that maximizes the volume of the box, right? Which I just told you from the calculus. Remember, I just told you it would maximize at 2 centimeters, right? Boom, right, 2 centimeters. It maximizes the box, right? Hold it. So I'm going to go buoyant force is equal to, I'm going to do some dimensional analysis right here. I got rho of, I'm going to call that okay, I'm trying to get newtons, force in newtons. So maybe 1,000 kilogram per cubic meter. Right there's my density of water. Volume of the box is, I'm getting 128, but that's in cubic centimeters. So careful about that. Right, I'm getting kind of mix and match in different type units. Right, and then I got a gravity field. I'm going to round to about 10 meters per second squared. Right, now this would give me newtons, except that volume isn't in terms of meters; it's in terms of centimeters. So I need to convert. So let's do some dimensional analysis stuff right here. Right. Guys, how many centimeters in a meter? 100 centimeters and 1 meter. And since it's cubed, I just repeat that step 3 times. So to the power of 3, right? Equals. Right. Let's see what I'm getting out of this. What is 1,000? 1,000 times 128 times 10 divided by 100 to the power of 3. Right. That's telling me 1.28, and the unit would be newtons because I'm talking about a force. That goes right here. 1.28 newtons, right? Which, by the way, how much lab weight would that be? Here's 100 grams. That's about a newton. Here's another 20 grams. So just a little bit more than this, right? So how much could that aluminum square hold if you fold it correctly? Right. It's just a little bit more than this. It's going to max out. Okay. All right. Guys, good so far? All right, let's check out these graphs on the back. Graphs on the back. All right, so what is y in terms of x? Remember, the more you fold up a side x, y is going to always shrink, right? In fact, it starts out with 12. If you don't fold up the side at all, 0, 12 is a single point. Isn't that true? If you don't fold it all, then the square is 12 by 12 centimeters, right? And the most you could ever fold a square is, well, you could take it all the way up to 6 centimeters. At that point, you just fold this right in half. And then y shrinks all the way to 0. So this point also says 6, 0. Right? Do you guys think that there's a straight line relationship between those two? And what is the equation of that line? Well, 12 minus the slope of that's like 2, 2x. Hey, there's the equation right there. Y equals 12 minus 2x. Right? Y equals mx plus b type. Right? That's that. It's the same thing. Y equals 12 centimeters minus 2 times x. That's it. Y equals mx plus b. Okay. Right, guys, see that? Right, now the tricky graph. What's the maximum possible buoyant force? Right, and I scale this for you guys. Right. Now remember, if you don't fold the side at all, then you just have a flat sheet that's going to hold nothing. That means you have this point right here. Okay. If you fold x all the way over to 6 centimeters, then you just fold this in half. And again, takes the volume, and therefore maximum possible buoyant force to 0. So those are 2 points. Right? Guys, good so far? Right. Now, in the middle, it can definitely hold something, has some volume, possible buoyant force. Right. And where does it max out? When x is equal to what? 2 centimeters. Right. And that's going to correspond to 1.28 newtons. That's what I did with all this math right here. Right. 1.28 newtons it can hold. Right. Have those little lab weights. So at 2 centimeters folding, you get 1.28 newtons of weight it can hold. That's that point right there where it maxes out. Right? Right. Now, you could plot a bunch of other points. Right? So some of you guys may have done that. Right? Here's that. Right. Overall, it's going to create this sort of a upside down looking curve, right? Which again is not a parabola. Right? It's not a parabola. Right? Not a parabola. But some kind of upside down curve, right, that maximizes at the top. Right. Let me go back and say what I was saying before about the calculus step when I was saying, like, imagine what the curve would look like. Right. Because if you hold your ruler flush to the curve, you could say that the slope of this tangent line, right, is changing as x changes. See, it gets shallower, shallower, shallower. Right. And at the very top, the slope, guys, what's the slope of that tangent line at the very top? 0. Right. And then after that, it decreases. Right. So the fact that the slope is 0 at the top means that you can maximize the size of the boat with some optimal folding, right? That was kind of the idea behind this here calculus. That's what this says, right? So if you take calculus one day and you're taking derivatives, right? If you ever hear the term derivative, that's what I did from here to here. Take a rate change, set that equal to 0. That shows how you can optimize your box. Okay. Okay. Is your guys' name on your paper? Your name is on your paper? All right. Once you got your name on your paper, pop that in the grade tray, and you get points. That's a wrap on Valentine's Day.